Start with this problem. A steel wire of 2 mm diameter is fixed between 2 points located 2 meters apart. So now we have a case of vibration in strings. So let's say we have a string that is fixed at both ends, and the length of the string is 2 meters. That is 2 meters, and the steel wire of 2 mm diameter. So that's the diameter of the wire. The tensile force in the wire is 250 newtons. So the force that is being applied is 250 newton. So a force has been applied, that is 250 newton, to determine the fundamental frequency of vibration and the velocity of wave propagation in the wire. So if you just recall the vibration in the strings theory, so this was the starting of the vibration in the strings. So we had made some assumptions that the mass per unit length, that is the linear density, is constant and it is perfectly elastic. Gravity is negligible. Vertical displacement is small. So while solving that, we found the speed of wave, or velocity of wave. You can call it sound. If you can call it something else. You can call it speed of wave. That is equals to, sorry. So speed of wave, that is equals to under root tensile force divided by the linear density. So this, using this, you can find our first you can solve the part B first, the velocity of wave propagation in the wire. So we know C equals to under root tensile force divided by the linear density. We know the tensile force, that is 250 newton, but we don't know the linear density. So we know the density, linear density, sorry. So the linear density can be written as volumetric density into the area, because volumetric density is mass per unit volume into the area. So we have volumetric density into the area, right? Because volumetric density would be mass per unit volume, let's say kilogram per meter cube, into meter squares. So it will cancel out this one. So we will have kilogram per meter, that is linear density. So because the wire is made up of steel, right, the steel wire, so the density will be the of steel, that is 7830 kilogram per meter cube, into the area, that is a cross-sectional area, since the diameter is 2. So the cross-sectional area would be pi by 4 into 2 exponent minus 3 square. So that is the area. So if you solve this one, you will end up having a linear density of 24.5987 kilogram per meter. That's 10 exponent minus 3 into 10 exponent minus 3. So we have the linear density now. You can substitute that one here. It will be under root 250 divided by linear density, and if you solve this one, you will end up getting, so it will be 100.8124 meter per second. That is a speed of or velocity of wave in the string. Now the second part is the first part was the fundamental frequency of the vibration in the string. So if you just recall again the theory of vibration for the strings, and if you check out the solution, once you got the wave equation, you solve that using the separation of variable method, you reach the solution, and then because it was fixed at both ends, we input the boundary conditions for both of these, and once you substitute that one into this equation for the u of x, we end up getting an equation for the frequency, that was nc pi divided by l. And so since we are interested in the fundamental frequency, that is the first natural frequency. So n will be equals to 1. So we can write it as omega is equals to, sorry, n c pi divided by L. So n is equals to 1 into c, that is 20, that is 100.8124, 100.8124. We have just calculated into the pi divided by 2, that is the length of the wire. So we'll end up getting the first natural frequency, that is the fundamental frequency, and it will be equals to 25.0 or 25.2031 hertz. That's our fundamental frequency, or the first natural frequency. So you see, this is how you first understood the problem statement. That was a vibration of wire or the strings, and it was fixed condition. So you exactly use the solution that we have calculated earlier using that one. Even if it's a new boundary condition, you will again go back to or refer back to the same solution. Here you will refer to the same solution, and then you input the boundary conditions of respective string. If it is fixed, it is free or fixed, or it is fixed and mass at one end, so on and so forth. So you can substitute those boundary conditions, find out the solution, find out the natural frequency expression, and the others. So this is how you can solve that such problems. Now moving towards the next one, it's a bit complex. So let's say, what do we have here? A cable of length L and mass and this phi per unit length is stretched under a tension P, and one end of the cable is connected to a mass M here, and which can move in a frictionless slot. So it can move here, it's a frictionless slot, so there is no opposition to the movement of mass. And the other end is fastened to a spring of a stiffness K, as shown. Drive the frequency equation of transverse vibration of the cable. So okay, we just